Hello again, everybody, and welcome to Environmental Sciences 347, Climatology. Today is Lecture 11, where we finally go from just understanding the basics of climate, the overall climate system, to what can force the climate system in one direction or the other. In this case, we're going to talk about natural climate change, meaning how the climate changes without any impact from humans. But on that, it takes a very long time to happen, and we'll get into that very quickly. So, the question here, what forcings, whether they be external to the system or internal within the system, can bring about climate change or high variability over a large range of time and spatial scales, whether that be global, hemispheric, whether that be decadal, over centuries, over millennia, or even larger. So we have to look at things that will impact the climate in a big way. And of course, as they say, it's complicated. There's a big spectrum of both forcings and scales in time and space to make changes to the overall atmosphere, land, ocean system. You can change the composition of the atmosphere. You can change the surface features, vegetation, the albedo, orography, and that just means land, mountains versus coastline, that kind of thing. You can change how much water is on the surface. You could change how much ice is on the surface. You could change the large-scale wind patterns. You can change the cloud cover. All of these things will ultimately give you a change in the climate. So when we step back, we think about radiative equilibrium. We can do any of those things I just said on the previous slide and then wait until the atmosphere, Earth, the entire system comes back into a relative equilibrium. All right, there's not so much changing on the outside or within the system to change the overall temperature or precipitation or anything one way or the other. So that's when we say the system is relatively in equilibrium. There's not a change in temperature for the entire system one way or the other in the longer term, meaning decades. So again, some important factors to think about when we consider that radiative equilibrium. Externally, there's fluctuations in the solar energy output. How is the sun doing? There's changes in the Earth's orbit around the sun because it's not a perfect circle. It fluctuates, which we talked about with the Milankovitch cycles. We won't touch on that again today because it's that important. Volcanic eruptions, and actually they're more important if we have volcanic eruptions close to the equator. Variations in atmospheric chemistry, alterations in the Earth's surface properties. Again, whether that be ice, vegetation, desertification, you build in cities, whatever. And that goes back to certain human activities as well, which can fold into a couple of other of those things. And these things are on different time scales. Right? Air-sea evolution is millions of years. The air-sea ice interactions, they're much shorter, as are volcanism, El Nino, La Nina, the ENSO, El Nino Southern Oscillation, solar variability, those are shorter term things. But the orbital variations, and of course, as you might guess, plate tectonics, these things take a lot longer to have a big impact on the climate. So we're not going to get into all of those things, but we are going to touch on some of the most important. And the first one of those really being the sun. That is, the energy source, the initial energy source for driving the climate here. So any kind of variability in the output, energy output of the sun is going to have repercussions here on Earth. That's not a shock, all right? But what we've seen generally in numerical simulations, as well as a lot of the observations, suggests that we need about a 1% change in the sun's overall output to significantly affect the average temperature of the planet. I mean, the Earth, ocean, land system. Not just the air temperature, but the entire system. All right. And you could see fluctuations there since about 1980 through the mid 2005 timeframe. There are fluctuations on a scale of about 11 years. Those are the sunspot cycles. All right. But on the left side of the graph, you can see the solar output. That's in watts per square meter, or energy per unit area. All right. And it fluctuates, but it's not a massive fluctuation. You see there, it goes from about a minimum of 1363 to a maximum of 1368, and that's less than 1%. 1% of 1300 is going to be 13. So if we wanted a full-on 1% decrease, we would go from 1366 to 1353. All right. So we haven't seen that big, or a full-on 1% change in solar output, at least recently. And recently, I mean in the last couple of hundred years. If we think back farther in true geologic time, on the order of 4 billion years ago, we know from geological records, we look at radiometric dating, we can tell that the sun's energy was only about 70% what it is today, back 4 billion years. But even though the sun was not putting out as much energy, there was a lot more greenhouse gases in the atmosphere, more methane, less oxygen, and methane is a much more efficient, stronger, if you will, greenhouse gas than carbon dioxide. So if you've got a lot of methane in your atmosphere, you have got a hot house for sure. The sunspots themselves, they're just small areas of magnetic energy, if you will, on the surface of the sun. So they indicate a more energetic sun. They end up suggesting that there is more energy being sent away from the surface of the sun. So more sunspots can contribute to a briefly, on the order of a couple of decades, warmer climate. Fewer sunspots act in the reverse, could translate into a cooler global climate. But in terms of individual sunspots, they only last a few days. Now, when I say that they come and go in a series of about 11 years, there's this maximum and then a minimum in the cycle. In other words, you'll get a whole bunch that pop up for about a few years, and they kind of cycle back down, or not that many. Exactly why that is still not well understood. Right, but we do detect a solar cycle of about 11 years between high amounts of sunspots and low amounts of sunspots. And when we think about more recent times, this chart's back to 1880, when we look at the average the average terrestrial Earth's temperature in red, and then we look at the solar output or solar irradiance in yellow. You can see that these things are pretty well correlated until about 1960, 1970-ish. All right. And then the solar output actually flatlines, if you will, maybe even goes down a little bit. I mean, the average is in that thicker yellow curve, where you can see the ups and downs in that 11-year cycle, and the thinner yellow curve. Same thing with the global temperature average. The thicker average is in the red, and the fluctuations from year to year are in the thin red curve. But the point is, those curves are diverging after about 1960 or 70. The planet keeps warming, even though the solar output has flatlined in these last 50 years or so. So hint, hint, nudge, nudge, what's causing that? Well, we'll talk about that more next time. You might have heard about the Little Ice Age, which happened in the late 1600s, early 1700s. There was a large drop in sunspots that lasted for a few to several decades, about 70 years. And that coincided with a cold episode in Europe. And we say we know Europe because the records are just better in Europe than they were across the rest of the globe. There's also, it's largely understood that the magnitude of the variation in the solar energy still wasn't overly strong. It's not like the sun went dead, silent, quiet for 70 years. There was probably some amplification or reinforcing mechanism required to influence the climate. In other words, it isn't just the solar output by itself or the decrease in solar output by itself. What probably happened which we started to see more ice, especially in the northern hemisphere. And then in time, that became a feedback mechanism to keep things quite cold in Europe. Now, back to the orbital cycles, the Milankovitch cycles. Please go back and watch that PBS NOVA video if you haven't already, because it's extraordinary. It's only 5 minutes long, and it walks through these cycles, and it walks through sediment cores a lot better. All right, but the short version is this. You've got variations in Earth's orbit, which change how solar energy is distributed globally. All right, these things are caused by gravitational influences on Earth by other planets, really the large planets, Jupiter and Saturn. All right, because everything is rhythmic, everything goes in very predictable cycles in terms of planetary orbits. That's why we can go back and calculate what Earth's orbital cycles were in the distant past. So three main cycles: the eccentricity of the orbit, whether it was more of an oval or a circle; the changes in the degree of the axial tilt. You're probably brought up thinking that it's 23.5 degrees from the vertical, the Earth's axis, all right, when it actually fluctuates a tiny bit, between 22.5 and 24.5. And then the precession of the equinoxes, which means the direction that the Earth is tilted in space. All right, it's not this direction all the time forever. It kind of wobbles around like a spinning top. So that changes the time of year that we get summer in the northern hemisphere because of the tilt of the axes. All right, so these things will drive the larger term fluctuations over tens of thousands to hundreds of thousands of years. It doesn't change how much sun is coming into the Earth, but it changes how it's distributed. And because there's more land in the northern hemisphere, the biggest impacts are in the northern hemisphere, which is why we tend to have glaciations in the northern hemisphere in these colder periods or these glacial periods. All right. So again, the output of the sun isn't changing, but how that energy is distributed across the Earth changes. So don't worry so much about every single one of these wobbles, but you get the idea when you start to sum all these effects. All right. That's how you begin to see, well, how much solar energy are you getting at, let's pick a point, that's yellow, 65 degrees north latitude in the summer. I mean, you can pick a point anywhere, but we're trying to just get a general idea between the energy coming in through the precession of the equinoxes, the obliquity of the orbit, the eccentricity of the orbit, the obliquity of the tilt, the eccentricity of the orbit gives you fluctuations in the amount of energy coming in during the summer at 65 degrees north. And that in turn correlates reasonably well with the stages of glaciation. In other words, ice ages. All right. You go back to that video, you see them out pulling up those deep sea sediment cores, which give us the information we need when we look at the chemical composition of those cores, what the climate was like, given the eccentricity, obliquity, and precession of the equinoxes on Earth's orbit. On the much longer term, you can look at plate tectonics. I mean, you know how the continents have not always been in the same location that they are now. There's a very slow drift in where the continents are over the course of hundreds of thousands to millions of years. All right. So as the continents move and change latitude, that changes ocean basins, which will in turn change ocean currents. All right. And then that in turn will change the air-sea interactions at certain latitudes on the Earth, certain positions on the Earth, and then give you a corresponding response to the air temperature. All right, we know pretty well that during the time of the dinosaurs, it was a lot warmer at the poles, especially the North Pole, right? Because the continents were in a slightly different configuration than they are today. All right, so plate tectonics also is one of these natural climate change impacts, but it is very, very slow compared to the human life scale, time scale. The plate tectonics by in addition to changing the ocean currents, the ocean basins, if you have continents smashing into each other, like India moved northward into Asia, smashing into Asia and forcing the Himalaya mountains to form. All right. These also change patterns of atmospheric circulation, clouds, precipitation. And over the longer term, it changes the weathering of rocks because of the changing weather patterns, and that can change the atmospheric composition of CO2. But weathering of rocks and that kind of stuff, that takes hundreds to thousands of years to occur. All right, so this is not something that happens in 100 years, to say nothing of a few weeks. So this is something that takes a long, long time. So when we talk about mountains, we can also in turn talk about volcanoes. Volcanoes do put carbon dioxide into the atmosphere, but it is not from burning carbon. It's from melting rocks. So that's more how we get CO2 in the atmosphere from volcanoes, and it's just not that much, at least in the here and now, compared to in Earth's distant past. So when you have very violent eruptions, all right, the volcanoes do, as you might guess, put a bunch of junk into the atmosphere. The most violent eruptions, all right, they can put ash, particulate matter, sulfate particles well into the stratosphere. All right. So you're talking about things that are up there more than 10 miles into the sky. And once they get up there, because the atmosphere and the stratosphere is fairly stable, it stays up there for a while. All right. So it creates a very thin veil, which will partially reflect more solar energy back out into space. All right. So it's not just a volcano here or a volcano there. You need big volcanoes, and typically close to the equator when we say low latitudes, because it's easier, I say relatively easier, because of planetary circulation, the atmospheric circulations. Once the soot, sulfate, ash, whatever, gets into the atmosphere near the equator at a very high altitude, it's more likely to be distributed globally as opposed to a single eruption, let's say up in Alaska, where that material is probably going to stay in the northern hemisphere. If you've got something that happens near the equator, and you think back up to the Hadley cell, something near the equator. So the equator, you got stuff going up, and then remember it goes both directions to the northern hemisphere and southern hemisphere. So you're having the ability to mix more of that particulate matter, soot, pollution, whatever, throughout the globe. And remember, most of the energy is coming in near the equator anyway. There's a lot more energy from the sun coming in at those low latitudes in the tropics versus the poles, which aren't getting nearly as much solar energy anyway. So when we think about the entire global energy balance of incoming energy from the sun, most of it is coming in at those latitudes. Let's say between the Tropic of Cancer and the Tropic of Capricorn. So this is why volcanoes near the equator are much more important than volcanoes like in Alaska or Iceland. Mount Pinatubo back in the early 90s did cause a bit of a response to temperatures, specifically in the northern hemisphere, because it belched so much stuff up into the atmosphere, and it hung out for about a year or two before finally settling out. It doesn't stay up there forever. It does settle out in time. But in the subsequent summer of 1992, it was quite cool. relative to normal. We did not have crop failures. We did not have freezes in July, but it was cool relative to normal in the summer of 1992. In fact, across the United States, it was the second coolest summer on record. And these are the anomalies. In other words, you can look at basically the darker blues or places that were coolest relative to normal. But those locations from Kansas to the Dakotas were about 7 to 9 degrees cooler on average during the summer. So if your average temperature was 70, this summer your average temperature was 61. All right, so that's a big shift over the course of 3 months. Remember, if you've got a small change in a temperature over a day, that's not a big deal. Small change in temperature over a longer time period is a big deal. That suggests there's some kind of forcing at play. All right, but it was cool through most of the United States, with the exception of the areas westward of the Great Basin. So, when we think about the volcanoes, and again, the location and intensity of an eruption matters. It's not just a volcano goes up here and there. An eruption is not going to change the mean temperature by more than about a degree for a year or two, unless you start getting a very busy volcanic planet. All right. The magnitude of a regional change in temperature may be greater, but when we think about the entire globe, a single eruption is probably not going to do long-term change to the climate. Back to the natural processes in terms of weathering and things like that, of rocks and plate tectonics, these processes do take a lot longer. The extinction of plants and animals have been linked to increases in CO2 associated with massive volcanic eruptions. Methane specifically was an important contributor to post-glacial warming at high latitudes, meaning the poles, the Arctic, Antarctic. Methane hydrates on the seafloor, emission from northern wetlands as temperatures rose. These are places where you can release methane. So methane is a very important contributor. Now, talking about methane today, unlike carbon dioxide, methane tends to settle out of the atmosphere more rapidly than carbon dioxide. But because it is such an intense greenhouse gas compared to CO2, that's why we're so concerned about what things are going on now in the Arctic. Permafrost specifically, there's a lot of methane hydrates locked up in permafrost. So if that stuff starts to thaw, you begin to release more methane into the atmosphere. So then thinking about the Arctic, and we think about ice in the Arctic, and indeed the Antarctic as well. And we know that ice is very reflective, so that plays a role, obviously, in the radiation budget or the temperature profile, the forcing, if you will, of the energy balance of the planet. All right. Remember that fresh fallen snow, new snow, typically reflects at least 80% of the incoming solar radiation, whether that be mostly visible, ultraviolet. So this reduces the amount of solar heating and lowering of the daily maximum air temperature. In other words, it doesn't get as warm during the day because you got ice all over the ground. Not a big shock. All right. Now, the changes in the regional snow cover will impact climate variability over the short term. But when you look at changes in Earth's sea ice or glacial ice coverage over multiple decades to centuries, well, then that has a longer lasting effect on climate. All right, so any longer term change in glacial or sea ice cover is going to affect climate. Again, this doesn't happen in the course of 3 or 4 years. This normally takes decades to centuries to develop. And this whole sea ice and temperature change thing is a positive feedback loop. And be careful here, because sometimes we hear the word positive and we think something that's good. In this case, a positive feedback just means it's something that continues to reinforce itself. It's not self-correcting. A negative feedback loop self-corrects and moves you back to your original state. A positive feedback loop keeps you flying off in one direction. So for example, when we look at the shrinking of Arctic sea ice, even though the melting of the sea ice doesn't really raise the sea level because it's ice that's floating in the sea. So when it melts, it doesn't change the sea levels, doesn't cause the seas to rise. It does trigger this feedback mechanism. So if you've got warming at high altitudes, 60, 70, 80 degrees north or south for that matter, you're going to start to see less ice. Makes sense. Things are getting warmer, so I've got less ice. Well, if I get less ice, that means I've dropped my surface albedo, which means I have less reflectivity going on in that part of the globe. So if I've got less reflectivity, that means I'm absorbing more incoming solar energy, radiation. So if I start absorbing more solar radiation, that means I'm going to get more warming. Which means if I get more warming, I'm going to start melting ice, which means I'm going to lower my albedo, which means I'm going to raise the temperature, which means I'm going to shrink more ice, which means I'm going to lower albedo. That's what we mean by feedback loop. All right, and this is kind of what we're starting to see play out in the Arctic already, unfortunately. So remember that Arctic sea ice does change through the season. All right, but it does exhibit long-term trends. On the chart here, you've got September versus March. September, you're getting to the end of northern hemispheric summer, so there is a relative minimum in the amount of sea ice that's over the Arctic Ocean. At the end of March, that's when you're coming out of the long winter, and that's where your sea ice is at a maximum. All right. So summer, you reach a minimum. At the end of winter, you reach a maximum. All right. So that gives you an idea of how much sea ice is typically in the Arctic in the summer versus the winter. But even in the summer, there is still some ice up there. All right. Just not as much as in the winter. It grows and contracts with the seasons. All right. However, having said that, when we look at what the average amount of sea ice is per month, no matter what month of the year you're looking at, it's on the decline. We have good satellite records back to 1979. And the graph you see here is the average sea ice extent in the Arctic during the month of March. And it's dropped from about 16 million square kilometers to about 14 and a half in an average year. Like anything else, there are ups and downs from year to year, but the overall trend is going down. And a lot of the projections suggest now that by the 2030s, the Arctic Ocean may be ice-free, at least briefly, during the summer. I mean, there's still ice there in the summer now, but we're seeing more and more shipping routes in the summer opening up in the Arctic Ocean that were not there 40 or 50 years ago. So ships can already begin to navigate the Arctic Ocean in the summer in places that they weren't able to 30 or 40 years ago. Well, that sounds great and all. That also has geopolitical ramifications for people who have an Arctic coastline, whether that be Alaska, whether that be Scandinavia, whether that be Russia. Russia's got a big, big, big coastline on the Arctic. These things matter. This is a chart, it's a complicated chart, so let's walk through this. But this is the Arctic sea ice extent through the course of the year, January to the left and the end of December on the right. The gray thick line, the darker gray thick line is the 1981 to 2010 median, or the middle. All right, the gray shading is what's called the interdecile range. In other words, 90% of all measurements are within that gray line since 1979. because that's how far back this goes. But 2012, which is the dashed red line, and 2020, which is the green line, are both lower than that. And if you look closely, the blue line, 2021, which only goes to April, you've got to look real close to see it there on the left part of the screen, that shows you what the Arctic ice extent is now, 2021. So you can already see that when we look at the record minimum in 2012 and then the minimum in 2020, there between September and October, again, the end of summer, when that amount of ice is at its minimum, that's down around 4 million square kilometers, where it was closer to 6 million square kilometers in the mean, or in the longer term average 40, 50 years ago. So we're losing ice. And we just don't see that changing until we make some changes in how we use energy. So anyway, and it isn't just the fact that there's less ice. One of the things that gets lost here, it's the amount of old ice that survives the summer melt is decreasing. I mean, there's always going to be ice up there in January. The sun isn't up in January. It's going to get cold. There's going to be ice there in January. All right. But when we look at the maximum ice cover toward the end of the cold season, let's say March, that's what we're looking at here. All right, on the top left is the sea ice age in March of 1985 compared to the sea ice age in March of 2019. Things that are orange, red, that's ice that is more than 4 years old. In other words, it survived the summer melt season. It didn't melt during the summer. It survived. Again, we still have ice up there during the summer, but the amount of ice up there in the summer is decreasing. So what we're seeing now during the wintertime is relatively new ice. Ice that's just formed as opposed to ice which has survived more than 2, 3, or 4 years. So as a percentage of total ice, that old ice, 4 years older or older, is decreased dramatically. There's just not much multi-annual ice up there anymore. More than half of the ice in the Arctic in the winter formed during that winter. And that shows us that the winters are getting warmer. The summers are certainly getting warmer because we just don't have as much long-term ice in the seas in the Arctic Ocean. Last time I taught this course was the 2012, or was right after 2012 minimum. And I wanted to contact the director of the National Snow and Ice Data Center, who specialty, of course, is sea ice because he runs the place. And they sent out a press release and I asked him about it. I said, can you tell us anything about the 2012 minimum? Knowing that our satellite records only go back to 1979. And his response was below. He said, it's correct to say that 2012 was the lowest ice extent since 1952, which is as far back as we can get with any reasonable confidence. And professionally, he'd say that 2012 was probably the lowest since 1900, being that our ice charts are not as reliable in earlier years because, 1900, there's not a lot of people running around to take observations. All right. When we think about climate, there's no reason to think that it was lower before that. I mean, there was a warm period in the 20s and 30s, but mostly the Atlantic side. There was a paper that came out recently suggesting that the current ice situation in the Arctic is lower than over the past 1,400 years. All right. And then when we think of longer term climate, about 7,000 years ago, there was this Holocene thermal maximum. And then during the last interglacial before the previous ice age. All right. But in terms of what's going on in the Arctic right now, this is not something that comes along very often. That's the short version. Finally, when we're talking about ice, we don't want to exclude the Antarctic, but it's important here to remember that the Arctic and the Antarctic are very different places. I mean, yes, they're both poles. All right, but the Arctic is an ocean surrounded by land. All right, ocean moderates climate. All right. The Antarctic is a big honking continent at the bottom of the earth. As a result, it can get colder. And because it can get colder than the Arctic, the jet stream winds around the Antarctic are stronger. Because the jet stream winds around the Antarctic are stronger, there's not as much mixing of air from the Antarctic to the middle latitudes in the southern hemisphere. So the cold air in the Antarctic tends to be locked into the Antarctic, right? Because immediately surrounding that is ocean. And that moderates climate. So you've got this local cold spot at the bottom of the world that gets colder and colder and colder and does not mix well with its surrounding neighbors 20 to 30 degrees away from the South Pole. So as a result, we don't see as much of a signal in sea ice around the Antarctic because there is no sea ice at the South Pole. There's sea ice at the North Pole. There's no sea ice at the South Pole. South Pole is land, and it's elevated land. It's a few thousand feet up in elevation. It's cold. It's dry. It's different geography. It is a fundamentally different place than the Arctic, and it's important to remember that. Don't expect to see the same results in the Antarctic as you do the Arctic, because you're not gonna. All right, so with that, we'll break, and next time we'll start talking more about anthropogenic, also known as human-caused climate change. You've heard all about it, and we'll talk more about how we know planetary warming is due to the impacts of humans running around and doing the things that humans do.